welcome everybody for this morning session. I did not introduce myself, I think, yesterday. My name is Roland Schnell. I'm a professor at TU Delft in the wind energy section, and I will also be chairing today the Airborne Wind Energy mini-symposium. We have, I think, 4 sessions, 2 in the morning, 2 in the afternoon, if I'm not mistaken, but it's basically an entire day. You can just stay here if you wish and get immersed in airborne wind energy. And this morning we have Professor Louis Bock from the University of Porto presenting something about optimal layout in airborne wind energy farms. So I'm pretty curious to hear.
Thanks, Roland, for your presentation. And we are addressing here the optimal layout in airborne wind energy farms. We will start with the introduction. Next, we talk about the problem formulation. It follows the methodology named random kinetic algorithms, which in our heuristic is based. Next, we present some computational results, and at the end we present some conclusions, and we will talk about future work. For each single airborne energy, we consider a conic-shaped flight envelope within which each unit can fly. The parameterization of this flight envelope involves various decision variables such as the elevation angle span, the maximum azimuth angle span, the tether length, and when we consider the problem, the turbine's location problem in the traditional wind farms, the main question is how far apart should the turbines be placed. The main constraint is related with the wake effect avoidance, and typically the separation between two consecutive turbines is between 5 to 9 times the rotor diameter in the predominant wind direction, while in the orthogonal direction to wind direction is from 3 to 10 times the rotor diameter. When we consider our problem, the airborne location in the unit location in airborne wind energy farms, the main constraint is related with the collision avoidance among kite and tethers. Here the wake effect is negligible, since that the wing area is much smaller than the swept area. But we can refer here the additional decision freedom. We have more decision variables, elevation angle variation, tether length, etc. In the airborne wind energy systems, we intend to have small elevation angles, which allow a better harnessing of the wind, and we also intend to have large altitudes where wind is more strong and more consistent. But these conditions implies that each unit can span a large ground area. For example, for elevation angle of 20 degrees and h of 20 meters, each unit can span approximately 1 hectare of ground area. So, an important question is how units can sharing common space. We can have disjoint ground areas. We also have disjoint workspace cones. That is the case which we are addressing in this work, but we also have an intersection between workspace cones. In the case 2 and 3, we have a more efficient use of the land, but it should be developed collision avoidance strategies. So our problem has various design parameters and decision variables. We highlight here the number of units to be displayed in the wind farm, the decision variables regarding to the flat envelope for each unit, the distance between units, the window distance, the transversal distance, that each unit should be operating, the average cycle power. In the problem formulation, we make some assumptions. We consider a full cycle with traction or reload phases and retraction or reeling phases. We also consider transition phases between the reload and the reeling phases with a fixed time and no production. The linear kites in the farm can work synchronously. It must be in the some phases of the power production cycle. Each kite fly in a circular trajectory. The kite should remain above the ground with a safety distance. The tether force should be strictly positive to avoid tether sag, and the tether length is bounded from above by a maximum tether limit. And we can define the instant kite position in the circular trajectory by a parameter sigma, and we use this parameter to define the elevation and azimuth angles as a function of sigma. And our objective function to be maximized is the average cycle power, given here in the equation 1, where we have the ratio between the energy produced in the reload phases minus the energy consumed in the reeling phases divided by the total time of a full cycle. Here at the T at the R are the efficiencies in the reload and reeling phases respectively. BTVR are the reeling out and the reload and the reeling tether speeds. The PT and PR are the average power production during the traction phases, that is given by this double integral with the variable sigma and the tether length. Here F is the ratio. F is the ratio between the kite radial speed and the wind speed. CR, the aerodynamic coefficient, is adjusted in the lift coefficient by the roll angle required for the circular trajectories. And the PR is the instantaneous retraction power given in this equation 3. We also consider various constraints, such as the maximum altitude constraint in equation 3, the minimum and maximum elevation angles in equations 5 and 6 respectively, the maximum azimuth angle constraint, etc. We also consider the distance between units. When we consider the orthogonal direction to wind direction, we have this distance d2 in equation 7. When for two consecutive units aligned in the wind direction, we have the equation H defined in Fagiani 2014, and we also consider the distance between the land boundary and the nearest unit. This is the minimum distance given in equation 9. If we assume there is no privileged wind direction, we can compute the distance d as a maximum between the distances d1 and d2, and we can explore two possible layouts, the squared layout in the left side and the hexagonal layout in the right side here. The number of units displayed in the wind farm with a squared layout is given in the equation n, and the number of units in hexagonal layout is given in equation 11. We are using genetic algorithms to approach these, to address this problem. In particular, the Weisel random genetic algorithms described in Gonçalves Rezende in 2011. And this approach has been successfully applied in various combinatorial optimization problems. And in BRKGA, each individual or chromosome is a vector of random generated real numbers in the SER1 interval. This algorithm has a Helix strategy in two phases. First, a percentage of individuals with best fitness is copied to the next population, and we also have a uniform crossover where the probability to choose an allele from the best parent is higher. We also introduce mutants that are individuals randomly generated to prevent a premature convergence of the algorithm. Here we illustrated the uniform crossover, where we can see that the parent one in the elite set, their alleles has a high probability to be selected. Then we also illustrate here the evolutionary dynamics of BRKGA. Percentage, 20% of individuals are copied to the next population. 60% of individuals are obtained by using the Bayes uniform crossover, and 20% of individuals called mutants are randomly generated to prevent the premature convergence of algorithm. Here we present in this flowchart. We present the main steps of our algorithm. Here we highlight the coding procedure, that is how physical solutions are obtained to given an individual chromosome. Next, we present some computational results. In our computational experiments, we consider a land with a length of 80 hundredths of meters and a width of 60 hundredths of meters. And we consider airborne with 1.5 kilowatt, a wing area of 0.28 square meters, and airborne mass of 0.7 kilograms, and we have the outputs for each wind speed. For each wind speed, we have in the square layout the values for decision variables regard to the flight envelope definition, and here we obtain 35 kites or units operating, and the respective average cycle powers in this table. The similar results for the hexagonal layout. For each wind speed we can see the values for decision variables, and here we focus the number of units is higher, is 45, and the respective average cycle power for wind farm with hexagonal layout. And when we compare the individual production of units, we can see that units in the squared layout has a slightly more production than units in the hexagonal layout. But however, when we compare the total production of wind farm, we can see that the wind farm with hexagonal layout has significantly more power production than wind farm with squared layout. But this is due mainly to the number of units operating. We have more units in the hexagonal, in the wind farm with the hexagonal layout. Some conclusions. The individual kite units in square layout produce slightly more power than each unit in the hexagonal layout. The hexagonal layout allows to have average cycle power significantly larger than in squared layout. But the kite wind farm with hexagonal layout overcomes the squared layout, mainly because it allows you to have a greater number of kites operating. As a future work, we tend to study the power averaging strategies, such as the units operating in the synchronized way with different time phases. We also intend to investigate impact of various kite form layouts on the total power production, and to estimate the levelized cost of energy for airborne wind energy systems in the Portuguese context, taking into account the cost of materials in Portuguese context. And so, some references, and I finished.
Thank you, Luis, for this very interesting presentation. I think we need more on this kite farm layout optimization. It's a very important topic. Are there any questions from the audience?
Yes, I was curious. At the beginning, you mentioned that you weren't considering the wakes of the kites. Is that right? Or why do we see a difference in the power generation per kite in the different layouts? If the layout, to my understanding, is only looking at how many kites we can sort of fit in a given area, or did I misunderstand something there?
The kite, or the difference in kite, or
So there was a graph towards the end where you showed the average production per kite, and I was just wondering why that would be different in the different layouts if you weren't considering wakes and stuff like that, or were you considering wakes, etc.
we have here the individual production of the kites in the square layout overcomes the slightly more production left than the kites in the hexagonal layout. However, in the hexagonal layout you have more units, and consequently you have a more production in the farm, the total production of farm. I don't know if it's exactly your equation. I have some difficulty.
Yeah, I think I understand. The point is you have a different number of units in a certain area, and you divide by that, and that might be the change.
Oh, so that's how it's cut.
The length, I think, assumption is
You have here in these figures. But we have 10 more units. But we are considering no privileged wind direction.
Good. I think it's clear. Thanks. Any other question? No other question? Then thank you again, Louis.
Thank you.